Today we're going to learn about how to calculate the energy of phase changes and of changing the temperature of different substances, okay? So this is where we ended last class. That's not on the pen. We ended here last class. So this is going to be the first formula we're going to learn today, okay? I call this Q equals MCAT because it's Q equals MC delta T. What does delta mean? Change, and it's a big triangle, so it kind of looks like a capital A, so MCAT. All right, so whenever I say Q equals MCAT, I'm talking about this formula. Q is heat. Heat is going to be in the units of joules. Okay, it's the energy in the form of heat. M is mass. What unit do you think mass is in? Grams. C is specific heat capacity. That's going to be in the units of joules per gram degree Celsius. This is a constant that you'll either be solving for or you will be given. What specific heat capacity means? It's the amount of energy required to raise 1 gram of the substance by 1 degree Celsius. Okay, so every substance has a different specific heat capacity. Every substance has a different specific heat capacity, and it basically tells us how much that substance will retain the heat or how resistant it is to changes in temperature. All right, so everyone reach down and grab your chair leg right now. Grab your chair leg. How's it feel?
What are you looking at me for?
Your chair leg, guys, your chair leg probably feels cooler, right? Feels on the colder side.
Sure.
What temperature do you think that chair leg is at?
54.
47 degrees Celsius is actually very warm.
Yeah. You're wrong.
47 degrees Fahrenheit. You think it's that cold?
Yeah. 60 degrees. 52.
Jacob, what temperature does that thing say?
37 degrees.
What is it? 22.5 degrees Celsius? That is the temperature in this room. Do you think that the chair leg is greater than, less than, or equal to the temperature of the room? Equal. It's been sitting in this room for over 2 years. The chair leg is not any colder than the room is. Why does it feel colder? That's because the metal that the chair leg is made out of has a very low specific heat capacity, which means that you can stop holding the chair leg, which means it transfers. I thought you were still holding on to the chair leg. Because it has a low specific heat capacity, it means that it transfers energy in the form of heat very easily. And as soon as you grab it with your hand, which your hand is at a warmer temperature than the room because our bodies are about 98.6 degrees Fahrenheit, not Celsius, degrees Fahrenheit. And this room is probably around 70, 72 Fahrenheit. Our bodies are warmer than the chair leg, so heat starts transferring from your hand to the chair leg, which makes it feel cold, right? Whereas if you were to touch something else, like your paper, is probably a lot warmer, okay? Another way to think about it. Have you ever gone to the beach in like June and then gone again in August? Maybe? Possibly? What do you notice about the temperature of the water? It's a lot warmer in August because it's had all that time to heat up. Water has a fairly high specific heat capacity, which means it takes a really long time relative to other substances for it to heat up, but it also retains that heat for a lot longer. Okay? How many of you went with us in the fall to Wallops Island? One of you. Okay. we used to go to Wallops Island around this time of the year. That's the AP Bio, AP Environmental trip. We used to go around this time of the year. And while the air temperature was starting to get a lot warmer, the water was still very cold. And it was kind of miserable. Now we go in the fall. Granted, the bugs are a lot worse in the fall, but the water is so nice when we get in it. It's a lot warmer than it is now. Another example. How many of you have ever cooked
Pasta. Yes. I'm so good at cooking pasta. That's the only thing I can make, but I'm so good at it. Yeah.
anyway?
Like cheese,
How many?
Alfredo, butter, steak, pasta sauce, anything.
Not where I was going with that. How many of you ever cooked something in the oven and you've had aluminum foil maybe covering your dish? It might be a pasta dish, I don't know. But how many of you have ever had aluminum foil covering a dish in the oven? Right, and when you take it out, have you ever touched the aluminum foil? It cools down very, very, very rapidly. Almost to the point where you can take it, you can remove the aluminum foil pretty much as soon as it comes out of the oven. That's because aluminum has a very low specific heat capacity. It transfers energy very easily, okay? So the higher the heat capacity, the higher the specific heat capacity, the more that substance will resist changes to its temperature. The more energy it takes to actually change its temperature. So it changes temperature a lot slower than something with a lower specific heat capacity. Okay? And then delta T is change in temperature. That's going to be in degrees Celsius. And it's always final minus initial. The final temperature minus the initial temperature. The temperature you end at minus the temperature that the substance starts at. Okay? So let's do some practice problems with these calculations. So this first one, how much heat is required to raise the temperature of 789 grams of acetic acid from 25 degrees Celsius to 82.7 degrees Celsius? And we're told that the specific heat capacity of acetic acid is 2.05 joules per gram degree Celsius. Okay. So, Q equals MCAT. That's the formula. Remember, Q is heat. What is our heat for this problem? That is our unknown. That's what we're going to be solving for. And that's going to be in joules. M stands for what? Mass. What mass of acetic acid do we have? 789 grams. C is the specific heat capacity of this substance. It's given. And it is what? 2.05, and that's joules per gram degree Celsius. And then delta T is the final temperature minus the initial temperature. So what temperature is this substance starting or ending at? 82.7 degrees Celsius, right? And it's starting at 25 degrees Celsius. For the sake of sig figs, I'm going to add a significant figure to that initial temperature just to make it easier. Okay? So what is that change in temperature? 57.7 degrees Celsius. Exactly. So now we're just going to plug everything in because we're solving for Q. We just have to multiply everything. (789 grams times 2.05 joules per gram degree Celsius times 57.7 degrees Celsius. How many sig figs will our answer have? 3. Always use the mass and the temperature for sig figs. Specific heat capacity, that C value, is a constant. So its value will never, its sig figs will never limit the number of sig figs to your problem. Temperature and mass. But both of our temperature and our mass have 3 sig figs, so we're going to just use 3 sig figs. So what do you get as your answer? A really big number, yes. What'd you get? 93,000 300 joules. That's a lot of energy. But if you think about it, it's a fairly large mass. Like the sample of acetic acid we're using is fairly large. And it's going up by almost 60 degrees Celsius. Its change in temperature is fairly high. One thing I meant to say about delta T is because we're always doing the final temperature minus the initial temperature, it is possible to have a negative delta T. If you're cooling a sample down, your delta T would be negative. And that would make Q negative, and that's fine. That's actually correct, because when Q is negative, that means you're removing energy. That happens when you're cooling something down. Questions? Let's do the next one. As the temperature of a piece of copper wire with a mass of 95.4 grams changes from 25.0 degrees Celsius to 48.0 degrees Celsius when the metal absorbs 849 joules of energy. What is the specific heat capacity of copper? So same formula, Q equals MCAT. Let's identify our variables. What is Q for this problem? (849 joules). Okay. What is M? 95.4 grams. C is what? Unknown. And that's going to be in joules per gram degree Celsius. And then delta T. How are we going to calculate delta T? 48.0 minus 25.0, which is? Yep, 23.0 degrees Celsius. Okay. So what variable am I solving for in this problem? C. So let's rearrange that formula to solve for C. When I rearrange it, what do I get? Yep, Q over M delta T, so Q over MAP equals C. So now we're just going to plug everything in. So see how you can solve for any of the variables, really. So 849 joules over Now make sure when you're doing the division, you divide, when you're doing the math, make sure you're doing all the functions properly. Make sure you're dividing by 23 instead of multiplying by it. You can solve that error by just putting extra parentheses around the bottom, around the entire bottom. Also notice that we have joules divided by grams degrees Celsius. That's what gives us our units for specific heat capacity. And with this, normally we don't worry about the sig figs of specific heat capacity, but that's really only when it's given to you. When you're solving for it, just use your lowest number of sig figs from the problem, which would be 3. Again, in this problem. That's a decimal point. All right, what do you guys get? Yep, 0.387, and again, that's joules per gram degrees Celsius. So according to this problem, that would be the specific heat capacity of copper. I don't actually know if that's the real specific heat capacity. I didn't actually check to make sure the numbers worked out where we actually got the correct one. But more of the process. You know how to solve for specific heat capacity if given the other components. Okay. Questions on 1 or 2 before we move on to number 3? All right, what do you notice about number 3 that might be important to make note of? It is similar to the calculations you will do for your lab. In a few classes next week, next Wednesday, I believe, we are going to be doing a lab where we are going to do exactly what it's saying here. We're going to take a sample of a metal, which you're not going to know what metal it is made of. You're going to find the mass of it. You're going to heat it to a certain temperature, and then you're going to transfer it to a coffee cup that's going to have, instead of a beaker, it'll be a coffee cup that has a specific amount of water. At room temperature, you'll know the temperature of the water, you'll know the temperature of the metal, and you'll mix them together, and you'll see what temperature it raises to. So. We need to bring our own coffee cup? No. So we actually have two systems going on here, okay? We have the metal, and we have the water. Which system in this whole process, like when you mix them together, which system is losing energy? Which system is losing energy? Which one? The metal. The metal is losing energy in the form of heat. And therefore, what is the water doing? It's going to be gaining energy in the form of heat. Where's the water getting the heat energy from? The metal. So there's a transfer of energy from the metal to the water. That's what causes the metal's temperature to decrease. Its delta T, it's ending at the 27.6 degrees Celsius. And it's starting at what? What temperature does the metal have initially? So both of them, when they're mixed together, it reaches a temperature of 27.6 degrees Celsius. The metal decreases temperature, the water increases temperature. And that happens when the energy is being transferred. So what is the delta T for the metal? Negative 71.5. It's negative because it's losing energy. It's exothermic. And then the water is gaining energy. Its delta T is 27.6 minus, what temperature did the water start at? 21.4, which is, what's that change? It is endothermic, but what's the actual value for the change? It is 6.2. Okay? Now notice the water only increased a little bit, whereas the metal decreased temperature a lot. That's because the metal's heat capacity, the specific heat capacity of the metal, when we do this whole calculation, it should be less than the specific heat capacity of water. Because the water only changed temperature a little bit, whereas the metal changed temperature a lot. Okay? All right, so in order to figure out the specific heat capacity of the metal, because that's what the problem is asking, we need to first know how much energy the water gained. Okay? Because all of the energy that the water is gaining should be equal to the energy that the metal is losing. We are making one huge assumption here, though. We are assuming that none of the heat energy is being lost to the surroundings. Okay? In reality, that is actually happening, but we're ignoring that. We're ignoring heat loss to the surroundings for the purpose of doing the problem. Okay? If you take AP, you correct for that factor. Okay? All right, so we're going to have to do Q equals MCAT twice for these problems. So we're going to do it once for all the water information. So what is the mass of the water that we used? What is it? 50 yep, 50.0 grams. Now, I meant to give you the specific heat of water in this problem. I just forgot to type it in there. But it is 4.184 joules per gram degree Celsius. That's going to be one of the highest specific heat capacities you'll see. I know it doesn't seem very high, but it is one of the highest. Okay. And then the delta T we already calculated to be 6.2. So go ahead and calculate the Q for water. How many sig figs will that Q have? 2, because that delta T only has 2 sig figs. What did you guys get? You should have gotten 1,300 joules, right? Or 1,300. Okay. So now, this is the energy that the water gains. Where did that energy come from? The metal. Okay. So, Q water equals negative Q metal. The amount of energy the metal loses is equal in sign, equal in magnitude, opposite in sign to the Q of the water. Okay, because remember, the metal is losing energy, so Q needs to be negative. The water is gaining energy, so the Q is positive, but the actual values are the same. Okay, so now in order to find C of the metal, we're going to do Q equals MCAT again, this time solving for C. Okay. So this is like number 2, where we're going to do Q over MAT equals C. Q is negative 1,300 joules. What mass of the metal did we use? Mm-hmm. 65.02 grams. And its delta T was negative 71.5. So since we have 2 negatives, we have negative joules and a negative delta T, the negatives are going to cancel out. Okay? You'll never get a negative C or a negative M. If you do, you've done something wrong. You either dropped a negative sign or you added one where you didn't need one. So go ahead and do that math. And remember, should this specific heat capacity be greater than, less than, or equal to that of water? It should be less than that of water because it's changing temperature a lot more. What did you guys get? Yeah? You should get 0.28. Make sure did you put extra parentheses around the bottom? You're off by a factor of 2 if you got 0.14. So you can recalculate it, and we can double check that. But this is how you do it. So make sure you star this problem. So next week, when we do this lab, I'll reference this problem again, but this way you all have it. Make sure you know how to do it, okay? All right, moving on. Now I'm really moving on. Before we move on to the next type of formula, I want to go back to this heating curve that we were looking at last class. So remember, we had these sections here. What can be said about the 3 sections I just highlighted? What is the same? What's similar for all 3 of those sections? What? Increasing or decreasing the temperature, right? What else is true about those 3 sections? What did we label those sections with? Not phase changes. Hmm? These were not the phase changes. Yeah, the sections I've highlighted in orange were not the phase changes.
The one that's where the temperature's changing to change.
We already established that's when the temperature's changing. What about the phases can be said about each of those?
They stay constant.
Yeah, each of those sections is when the substance is all in one phase. Remember, this first one is where it's in the solid phase, liquid phase, gas phase. You were on the right track. You just said water instead of liquid. Brody, you were on the right track. You just said water instead of liquid. So, you were there. All right, so this portion here, well, actually, for all three of these sections, in order to calculate the energy for that change in temperature, we're going to use that Q equals MCAT formula. So if the substance is all in one phase and it's only changing temperature, then to find Q, you'd use Q equals MCAT. Along the phase changes, which remember were the plateaus where temperature is staying constant, we can't use Q equals MCAT because delta T for those sections is what? For the two sections I highlighted in yellow, what is delta T? 0. Temperature isn't changing, but there's still heat associated with those transitions, okay? So for those sections, that's along the phase changes. We're going to need a different formula for that, okay? Which is Q equals N delta H. Q equals Na, okay? Where Q, where Q is still heat, but this time, because of the way the problems are designed, this heat is going to be in kilojoules. Okay. N is the number of moles. Remember, just like in the ideal gas law, PV equals nRT, N is moles. Here, N is moles. And then delta H is the change in enthalpy. It's like C, where it's a constant. It'll either be given or you'll be solving for it. Okay? And this is going to be in kilojoules per mole. And this is the change in enthalpy is basically the change in the heat associated with a phase change. Okay? Before we do some practice problems with this, we're going to fill in the chart that's towards the bottom of this page. Are we ready? All right, so let's think about our phase changes. One of the phase changes is going from the solid to the liquid phase. What would that be called? Going from solid to liquid? Melting, right? Does it have another name that maybe we learned last class? Not freezing. It does start with an F. Fusion.
Sorry, I was like thinking from the...
Yeah, we'll talk about freezing in just a little bit. So, melting or fusion, same thing. In order to melt a substance, do you think you have to put energy into it or take energy out? You have to put energy in. In order to like melt ice, you have to heat it up, right? You have to put energy in. So does that make it endo or exo? Endothermic, because energy has to go in. So what sign would that delta H have? Positive. And that's going to be positive delta H fuse. Positive delta H fusion. So it has the subscript FUS for fusion. The opposite process, going from liquid to solid, is called what? Freezing. Which is also sometimes called solidification. In order to freeze a substance, do you have to put energy in or take it out? Take it out. Hence why you put water in a freezer to freeze it, because that will remove heat from the water versus putting it in the microwave. So that makes it what? Endo or exo? Exo. If we have to take energy out, it's exothermic. Now, the delta H for freezing will have what sign? Negative, but it's going to be equal in magnitude to delta H of fusion. So we're going to say this is negative delta H fusion. Equal in magnitude, opposite in sign. Okay? Another phase change. It's going from like the liquid to the gas phase, right? What's that called? Vaporizing, right? Which can also be called boiling or evaporating, but I'm going to use vaporizing as the big general term. Do you think that's endothermic or exothermic? Think in order to boil water, you have to put energy in, right? Endo. So what sign will its delta H have? Positive. And this is going to be positive delta H VAP, or vape. Oh, we're talking about joules and vapes today. Ooh. Opposite process is gas to liquid. What is that phase change called? Condensation, or if we're using the ing form of it, it'd be condensing. Endothermic or exothermic? Exothermic. We have to take energy out. How would you describe its delta H? Negative delta H vape. Negative delta H VAP or negative delta H vape. It's the same amount, same quantity as the vaporizing one, opposite in sign. And then the last little bit, we're going to go solid to gas. Does anyone remember what that is called? Sublimation or subliming. Which one do you think this is, endo or exo? Endo. You should be picking up the pattern with these phase changes. What sign will that delta H have? Solid? The only positive, delta H sub. And then the opposite process, what's that called? Deposition. In the ing form, it's depositing. Think the gas is depositing in solid form. Endo or exo? Exo. And then what would that delta H be? Negative delta H sub. Notice how the subscripts for all of these were the same for opposite processes. The signs were just different. The signs were opposite. Okay? Okay. No, actually, I'm looking at the fact that we have a lot of time left. All right, 2 more problems and then we'll be done. All right, how much energy is required to melt 115.0 grams of ice? And I've given you the delta H fusion for water is 6.03 kilojoules per mole. So we're using Q equals Na. Q is what? That is our unknown. That's going to be in kilojoules because of the delta H is in kilojoules per mole. What is N? What does N stand for? Moles. Do we know the moles of this substance? No, but can we find the moles? Yes. How are we going to find moles? Grams to moles using mole conversion. How do we go from grams to moles? NM on the PT. So we're going to take 115.0 grams of ice. What's the chemical formula for ice? H2O. That often throws people off because they're like, wait, but what's ice? Ice is solid water. It has the same chemical formula. It's just in a different phase, different state. What's the main ingredient in orange juice? Water. Orange juice is mostly water. A lot of those juices are water. Okay. So we're going to do a mole conversion. I think it's already a thing. Sorry. What's the molar mass of water?
The orange juice. But it's like an ice cube.
How many sig figs?
It's not on a stick.
Guys, how many sig figs? 4. Look at our mass. It has 4 sig figs. So how many moles is that? What is it?
6.38.
All right, and then delta H. This is delta H fusion. Why is it fusion? Because it's melting. And that is given in the problem 6.03 kilojoules per mole. Okay? So now we're just going to plug into the formula. How many sig figs will our Q have? 4, because delta H is a constant, just like C is a constant, so it doesn't limit our sig figs. So for this, the only thing you're going to look at for sig figs is your mass, or your moles. Okay? What do we get? .48 kilojoules. So that's how much energy you would need to add to 115 grams of ice to make it melt. Okay? Which came from the sig figs from the math. Yeah, not always ignore sig figs from delta H. Yep. One more. Last one. Last one, last one. How much energy is released to condense 670.0 grams of water? And the delta H vap for water is 40.7 kilojoules per mole. So Q equals Na. We don't know Q. That's what we're solving for. It's going to be in kilojoules. N, how are we going to find N? Mole conversion. It's the same substance as the last problem, so the molar mass is the same. The setup is going to be the same. Different numbers. Same sig figs even. I believe when you do this, you get 37.18 moles. Can somebody verify that? That is correct? Good. And then delta H. Now, what phase change is occurring in this problem? What is it doing? It's condensing. What is condensing in relation to vaporizing? It's the opposite process. I gave you delta H vap, so delta H that we're going to use will be negative 40.7 kilojoules per mole. So this is VAP. And it's negative, I'll even put that in a different color because it's condensing. because energy is being released. Okay? So in order to solve this, negative 40.7. So our Q will be negative, and that's okay. The negative sign just means energy is being released. What do you get? Negative 1,513. Thank you. Kilojoules. All right, I'm going to stop the video now. Guys, I haven't stopped the video yet. Shh.